So hello all nerds, and welcome back to another episode of My PhD is Ruining Me. No, I'm just kidding. So for those who don't know me, my name is Jess. I'm a former mechanical engineer. Now I'm doing my PhD in environmental engineering, and it requires a lot of me tinkering with electronics, a skill that I did not have at the beginning of the year. But I am a little too familiar with by now, especially with isolation and social distancing. So over the last year, what I've been trying to do for my PhD is build an open sourced, open hardware, affordable turbidity sensor. And the last time I made a sensor update video, I was basically showing you how I created the technology using detectors, using infrared LEDs, some filters, some lenses, and I ordered this calibration liquid so I could do a proper test of my technology. So this sensor is bare bones. I have it right here. I'll show you it in a second. It's not waterproof. It doesn't have an SD card. It doesn't even have a power button. It needs to be plugged into my computer to work, but I just wanted to test whether the technology works or not. And last time in August, quite a long time ago, when I put out my last video, I was having so much trouble. I could not get consistent results. I would pour in this stable calibration liquid and my sensor would give me different readings every single time. There were a few different ways that I went about fixing this problem. So the first thing is that I actually played around with the formazine, the calibration liquid, a bit more, and I discovered that it's super sensitive and it just needs a lot of patience, first of all, and really a lot of patience, sometimes just hours of staring at it and doing other work, while if I mixed it up too much or too fast, then it had bubbles and I had to wait for the bubbles to escape. So that's the first thing, patience with the calibration liquid. And then the second thing that I discovered is I just had my entire thing laid out on a breadboard. It didn't look like this. It looked kind of like this. I mean, this is another version that I'm playing with now, but it was just not stable at all. So the way I went about this is by actually soldering or soldering, I will never know how to say this word properly, my development board to prototyping board with the resistors connected to all of the LEDs. So you can just see this is a prototyping board. Here are all of my wires. They're all connected really strongly. And then here in the back I have, ground and power. Ignore these. These are for another version that I'm playing with now, not at the time of recording this video. And I did this basically, the soldering, this playing around with the formazine, to see if I could reduce that noise that I was having so much trouble with back in August. And after implementing these two things, now looking back, it seems like such easy fixes, although it took me so long to get there, because that's just the nature of problem solving. You just gotta try and try and try different solutions until you find the ones that work. And after all of those months, I did it and it worked. It worked. I was able to pour in different dilutions of my formazine into my sensor, and I could always read the same results consistently over and over again. So what I want for my sensors, I want it to give me a full range of 0 to 4,000 NTU. If you don't know what NTU is, it's basically just a randomly selected turbidity unit. It has no SI significance. Most of these sensors operate from 0 to 4,000 NTU, and so I want to copy them. I want to be able to reproduce what they do. So I know I've tried to explain this a few times, like the technology behind my sensor, but now that I have these diagrams that I created for my presentation, I figured it would be even easier to explain to you now how this sensor works. So here you can see this is the principle. This is my cell, I have my RI light, and I have two detectors, and then here I have the sample cell. And this, basically what I wanted to do is I wanted to investigate what kind of effect does adding a lens have on my sensor. Like, do I get better results when I add a focusing lens? Because most of these expensive sensors use lasers, but obviously since I'm creating an open hardware version, using a laser isn't like battery optimal, energy saving. It's just dumb. So I wanted to see what kind of effect adding lenses would have. Then I wanted to have, because there's a lot of theory behind like the transmission of light and at what angles it's being detected at, and yeah, how that changes when you have more cloudy water. So I had created 3 different sample cells with these 3 different architectures, and I wanted to see if I get more accurate results using one or the other, or the third one. Then the last thing I wanted to do was, because I'm actually, this diagram doesn't have my lenses here. Okay, there should be lenses like this here. But since my sensor is going to be exposed to, you know, it's going to be underwater, but it's still going to have sunlight reflecting from the bottom of the river coming up into it. So I wanted to know what kind of effect does ambient light have on my results. So I wanted to see if there's a difference in my readings if I add IR filters. I'm really proud of these diagrams, and I hope I'm able to actually explain this better to you now that you have these visuals. And so, you know, like that's the whole thing about, you know, science. You have to come up with like a hypothesis and test your different theories. And so that's what I'm trying to do here. I designed this experiment, and I knew that based on my results, I will have an answer. And sometimes the answer is inconclusive, but an inconclusive result is also a result. So I'm really excited because I just processed my data from my first experiments, and they look exactly as they should, as if I was using an expensive sensor. So let me show you. These are very rough cuts, or rough plots, but they look good. So this is what all of my curves should look like. So this is NTU versus amount of light reaching the detector. So here I have frequency, and frequency in my case is proportional to the amount of light hitting the detector. So for example, for the 90-degree detector, it looks like this curve, and that's exactly what I have here. And then in my third sample cell, this is sample cell number 2, this is sample cell number 3, it has the same curve. For sample cell number 4, I switched out this detector for a backscatter detector, which should be doing this, and that's exactly what I see here. And then with the forward detectors, so the forward detector is this curve, it goes up and then it comes down, and that's what I see here, and that's what I see here. And this one, it didn't work because I actually used a transmitted detector, which means it starts off really steep and comes down, and I think my detector, actually this is its limit. So that's why it's capped off here and then it comes down. So that makes me really excited, and now I just have to pick which one is more accurate. These experiments I was able to finish, and I was able to show them just in time for my research plan presentation, which was in September. And so I don't know if every university does this, but my university, within the first year of your PhD, you have to present your research plan. So it's what you're going to carry out for the next 3 years, and it needs to be approved by a board. And the board is like senior scientists or other professors from different universities or different departments, and also your PI is usually there too. So I got my results just in time, and I showed it to them, and everyone was super happy with the results. So after I showed these to my professor, we both agreed that with more data points, I can actually get better results. It's after my trip to the Viosa, and I am back in the lab doing some more experiments. I wanted to do them closer to between the 0 to 10 NTU range because I had just the data point 0 and 10, and so I wouldn't be accurate enough in that region. So I wanted to get proper data, so now I'm doing those experiments, and I have this tungsten light bulb, which are banned in the EU from selling, but I saw it in a display at a store. It was giving off a lot of heat, so I stole it because I had no idea how to get this light bulb otherwise. Basically, why I needed a tungsten light bulb is because it gives off a lot of IR light, and the sun gives off IR light, so this is my best approximate for sunlight, because I have those little IR filters that block out everything faster than 550 nanometers. So I wanted to see how IR light affects my measurements. So that's that. That's the cheapest solution I came up with. Okay, it is day, I don't even know, in the lab. I am finishing up with my experiments. So now I decided to do more measurements in like the 0 to 100 range, and as you can see, I'm almost done. I'm at 60 NTU right now. My Microsoft Word my Excel stopped working, so now I'm using Numbers or whatever the Mac program is. It's terrible. I don't like it. Anyway, those are my beautiful pipettes. I had to watch a YouTube video about how to use those. And yeah. So this is why I've been gone for so long. Also, in the middle of all of that, between those new experiments that we decided to do and after my research plan proposal, I went to collect data on the Viosa. So there was also that in the middle. And then I had this giant new set of experiments that I had to do. So that's also where I've been. But the great news is that after all of that hard work, I got nice results in all of those ranges. And I'm able to predict turbidity quite accurately, which makes me quite happy. So here you can see this is like an example plot of my predictions from 10 to 100. So that makes me really happy. So now that the basic technology is down for the turbidity sensor, the next thing I have to do is, this thing has no battery. It has no SD card. It, basically it just outputs the two frequencies from the two detectors, but I need to implement the model in here so that it outputs NTU. It also has to go into deep sleep, so every 15 minutes I want it to wake up, take a measurement, and then go back to sleep, have a super, basically like a trickle charge current, and then the internal clock will wake it up and every 15 minutes take a measurement and go back to sleep. So that's so that it can conserve battery. So it needs a battery. Oh, it probably needs a power button. Probably implementing a power button would be cool. So power button, SD card. Oh, and did I say it needs to be waterproof? Yeah, so once all of that works, it will then need to be put into a cell that is waterproof. And then you could stick it in the water and it can take measurements. Oh, and did I say that I'm supposed to also implement a temperature and pressure sensor? Yes, but those sensors already exist, so it's just a matter of hooking up the pins to my printed circuit board. So those are basically my next steps over the next few months. Oh, by the way, did you notice that I'm in my childhood bedroom because I am now out of quarantine? I was in quarantine 2 weeks, coming home to Canada. Now I'm in my childhood bedroom, basically in quarantine because all of Canada is in quarantine, but at least I'm with my family, which is nice. I feel like that was a lot of information. I feel like I could also talk about this forever. So if you made it this far, thank you very much for watching, and please, if you enjoyed this video, let me know in the comments below. I like reading the comments. I try to go through them every week as you probably may have noticed if you've left a comment, and like this video if you like it, and please subscribe and hit that bell so that you don't miss my next censor update. And just thank you very much for watching, and happy holidays.